Hello! How good is that? Welcome, everybody. Thank you so much for being here. My name is Anna, and welcome to a Materials and Making Odyssey. What is that? We're about to find out. Welcome to the Royal Institution. As you've seen, this is a really a building that is steeped in scientific history, and it is such an exciting place for me to come and talk to you about my love for science. I found out recently that 10 elements from the periodic table were discovered or first isolated in this very building. Yes, correct. And when I thought up the idea of doing something like this, of putting on a big celebration of materials and making, the Royal Institution really was the thing that came to the very top of my head. You are going to see the hard work of so many different people here tonight, particularly the RI's demo teams. I've been throwing so many weird and silly ideas at them over the last few weeks, and their attitude has always been, yep, let's just do it. So I'm very, very excited to show you the results of that. Everything from propane, we've got liquid nitrogen. Every time I ask them for a dewar of liquid nitrogen, they come on and they say, also, did you know that James Dewar invented the dewar in this very building? It's a lot of fun. There'll be a lot of that here tonight. I'd like to start, though, by thanking all of the makers that you saw around the building this evening. Some of them have come from really, really far away to come and demonstrate their craft, and I'm so, so grateful to all of them. So can we give them a big round of applause before we start? Thank you. I also need to introduce you to my wonderful house band who are sitting in the front row. They're going to be interjecting at times. Sometimes I will ask them to do so if something is taking a while to heat up. This is going to be slightly ramshackle affair, so there may be some musical interludes while we wait for stuff to happen. But they've been practicing really, really hard as well, and guys, I'm so grateful for you being here, so thank you. Okay. So now that we've locked the doors, I'm here to tell you that this is a book launch. The RI told me that we're not allowed to tell people that it's a book launch before they buy tickets, because otherwise they won't come. So sorry, this is a book launch. This is the paperback book launch of my book, Handmade, A Scientist's Search for Meaning Through Making. The hardback came out in 2021 when it was kind of half COVID lockdown, half not. And so I didn't get to do any live events. So this is 2 years later, the first time that I've stood in front of a live crowd to talk about my little lockdown baby. So thank you for that. Tonight, my plan is to kind of really just tell you some stories from the book, and to show you kind of, well, hopefully my love for materials and making, get you inspired as well. So this book came about because I did an undergraduate in materials science, and I went on to do a PhD as well. And my PhD was in hydrogen storage materials, which until a few months ago, nobody knew what that was. And then the movie The Glass Onion came out, where an evil genius, Elon Musk type character, had a crystal of hydrogen storage materials and was planning to take over the world, which was annoying because that was my plan. So they've made a movie about that now, which is quite annoying because, I would have liked to have starred in that. But what I found, though, when I was starting to work on hydrogen was that I would come home and I'd tell my friends and family that I was working on hydrogen. And they either thought I was trying to solve the Hindenburg disaster or that I was building bombs, neither of which was true. In my mind, I was trying to save the world with green energy using hydrogen. But I realized very early on that public perception of science was going to be crucially important to the kind of success of my research. So I started getting interested in public engagement. I started off by doing stand-up comedy, and actually this book opens with my very first attempt at stand-up comedy is in the first few pages. You can probably feel the anxiety steeping through the pages. That then took me on to kind of learning about how to sort of understand audiences. That quickly took me to storytelling because I ran out of jokes about hydrogen, so I had to quickly start telling other stories. And I started kind of, like I said, getting interested in public engagement. And night after night, I would stand up and I would tell audiences what material science is. And I say something like this: what we do in material science is we like to zoom in, and we look at all sorts of stuff to zoom into: metals, plastics, ceramics, glasses, composites, substances from the natural world. And we zoom in all the way down to the scale of the atom. I'm not very good at drawing, by the way. That's sort of part of the book as well. We zoom in down to the scale of the atom. And we look for clues about why the behavior of atoms and what's going on down there can explain how materials behave at the kind of human scale, at the scale of the microphone, for example. And so we look at what element from the periodic table those atoms are. We also look at the forces of physics between them and how strongly they bond together or not. And then we also look at the engineering of materials, and so how these atoms form structures sometimes inside materials, sometimes in stuff like metals and ice. You will have atoms that are all lined up in a really neat and rigid and beautiful symmetry of the positions of the atoms in those materials. Whereas in stuff like glass and sometimes plastic, it's kind of higgledy-piggledy and a random mess. And all that stuff, the chemistry of the atoms, the physics of the bonding and the engineering of their structures, we use to explain why materials are the way we find them, right? So why a microphone, the casing of it made of steel, would mean that it feels cool to the touch because of what's happening in the atoms inside. Why steel is strong and hard and tough, and why we would build buildings out of it. And the behavior of atoms as well can explain why materials like rubber, for example, are soft and stretchy. And it's all to do with what's going on at the very tiniest of scales. Now, until a few years ago, this was all I really knew about the science of materials, right? Looking at the very tiniest of atoms and extrapolating that to materials' properties. Then I had what I can only describe as a crushing realization. And that was, it came about because I was working in the lab one day. I was holding this big, long, relatively expensive glass test tube. And I turned around like that to the wall, and this test tube just smashed everywhere. Now, this was not an unusual occurrence, I have to say, particularly in my lab. Stuff gets broken all the time. But what I had to do, having broken this test tube, was to go off to get it fixed. So off I went to the chemistry department to try and get this test tube fixed. And I knocked on the door of a very, very special person in the chemistry department, which was the resident glass blower. And I said, "Hello, sorry, please can you fix my test tube?" He said, "Yeah, come on in, I'll do it for you now." And so he sat down and he got his torch and he started heating the material. And I watched him as he did it and took some tongs and sort of coaxed this gooey, beautifully transparent liquid back into the shape of a test tube. And in that moment, like I say, I had a terrifying revelation, which was that by night I had been telling people that I was an expert in materials, right? What I've just told you, basically. But I had absolutely no idea whatsoever what this person was doing, how he was able to understand the temperature of the material, how it moved, how to relate, how to make it with his hands. I had no idea about that side of things. And so I thought, how can I stand up and tell people that I'm an expert in materials if I can't even do this? And so that set me off on a journey. And I set out and I talked to nearly 100 craftspeople, like potters and stonemasons and blacksmiths. You've met some of them tonight. Bakers, people that know about materials from a kind of hands-on perspective. Because what I wanted to do was to glean from them their knowledge base of materials and to hopefully fill in a bit of the gaps in mine. And then one day, a few years later, I went on a swimming holiday. And I met a woman called Laura. And we were sitting down at dinner one day, and Laura was like, "Oh, what do you do?" And I was like, "Oh, I've got a podcast." The podcast used to be called, it's called Handmade now, by the way, but in the early days it was called Real Talk, which is, it's spelled RIAL talk, like material. But a visual pun for an audio medium is not a good idea. So we changed the name eventually. But anyway, I was telling her about Real Talk, and she said, "Hey, if you ever want to write a book, then I could be your agent." She is a literary agent. She wasn't just like... Hey! And I was like, yeah, that'd be amazing. Oh my God, I'd love to write a book. And so she helped me to write up the book proposal, and then eventually my book came around. And so my plan is tonight is to tell you a little bit about some of the stories from this book, because when I came down to actually sit down to write this thing, I had another crushing realization. This is my life, guys, just crushing realization after another. I sat down to write this book and I was like, why should anyone care? Right? Why should anyone care about how the atoms and the engineering and the structures and the other properties, like, why should anyone care? And I thought, well, I care, and I care about this stuff because it influences my life, right? All of the materials around us tell stories in our lives. And so that was going to be my in. I thought, if I could show my readers the stories that these materials have created in my own life, then maybe it would serve as a bit of a mirror to my readers, and that they would then start to recognize the stories that were told by materials in their lives too. And so that's my plan for us together here tonight as well, is to tell you a few of these stories, and there's some books outside for sale afterwards. So let's start with where it all began, with glass. It's going to keep happening, so... So I went off on this quest to meet a load of makers and actually have a go, get my hands dirty with their crafts. And the first maker that I met was a glassblower. And this was a problem, though, right? This whole idea to go and meet these craftspeople and have a go and get my hands dirty, right? Because I was a scientist for a reason, guys. The reason was, as a very small child, I had an incredibly traumatic life event, which was, it's actually not, sorry to make that serious, it's not, it's kind of a funny and weird one. The traumatic life event involved, in my school arts and crafts lesson, we had to make cushions. And I wanted to make my cushion in the shape of my new pet rabbit, Daisy, who was like a lovely black and white rabbit, very, very sweet. And so I sat down, sharpened my pencil, drew the shape of a rabbit, cut out some fabric, stuffed it, drew a rabbit's face. Now, to be fair, you can't tell if this is just my artist's impression of the cushion or if it actually looked like this. My parents are here tonight and they can tell you. I think it's probably a bit of both. My artistic skills have not improved since the rabbit cushion, but my entire class fell about laughing at me. They pointed and laughed and said, "Ha, that doesn't look like a rabbit." And to be fair, it doesn't. But I was incredibly upset by this. Because, I thought of myself as a capable young woman who could do anything she set her mind to, apart from arts and crafts. So then herein lies my problem, right? I need to fill in the gap in my materials knowledge. It lies with the realm of the craftspeople, but how am I going to do that without getting my hands dirty and beating my nemesis of meeting my arts and crafts nemesis? So I set out and I met lots of different craftspeople. The first one was a glassblower. And I'm going to start off by telling you a little bit about what glass is. We'll do a little bit of material science, and then I'll show you kind of how glass works, show you what I learned from this glass blower. So glass is a material that's made out of atoms, like all of them are. In some materials, like metals and materials that are just kind of one thing, one element, the atoms inside those materials just kind of exist as themselves. But in other materials, like glass, the atoms form little groups of atoms, which are called molecules. And that's the case in glass. So the molecules in silica are silica molecules. There's silicons and there's oxygens in there. And then those little arrangements of atoms, those molecules, then form bigger arrangements inside different materials. Now, there's one weird thing with glass, and I'm going to show you what that weird thing is by heating up some glass and doing a little bit of glass blowing. So here's a Pyrex tube made of glass. And what I'm going to do is I'm going to start heating. I'm going to start heating this glass tube. Now, when you heat glass, you have to introduce it to the flame quite slowly. And I'll explain why in a minute. But you sort of want to bring it in quite far away, and then you have to rotate it as well as you introduce it to the hottest part of the flame. And the weird thing about glass is that glass doesn't melt. You always think of glass like when it gets soft, you'd think that that was molten glass, but technically glass doesn't melt, even when you heat it up and even when it's flowing around like a liquid. And the reason that glass doesn't melt is its atomic structure. So if you can see from my little diagram, the atoms in glass, the molecules in glass, are randomly oriented. Right, there's no real structure to them. They're just sort of in there, all higgledy-piggledy. And that's very different from other sorts of materials like quartz and ice and metals. In those materials, the atoms are in what we call a crystal structure. In crystal structures, there's a very neat order to it. There's lovely symmetry, as you can see from my little diagram of quartz. And so in those sorts of materials, like ice, we all know ice, when you heat ice to 0 degrees, it melts, right? And that happens because all of the atomic bonds in ice are identical. So at exactly 0 degrees, that's enough energy to make those bonds break and to form water. But in glass, it's different. In glass, there is no, all of the bonds have kind of different strengths. There is no one particular structure to melt. And so what happens is as you heat it up over a few hundred degrees, the bonds gradually break. And so the material goes from being a little bit hard, well, very hard initially, and then it gets softer and softer and softer until eventually it starts behaving like a liquid. But there is no one point, there is no one melting point. So I think I've got my glass hot enough now, and what I'm going to do, first of all, is just pinch it off. Okay, so now I've got a little pinch in this glass, there's a seal there. I'm going to heat it again and see if I can blow a little bubble, which is fun. So I'm going to heat it up a little bit along the side of it now. Can we have some musical accompaniment for this? Amazing, thanks guys. Okay, ready? I'm going to come around here to do it so you can see. It's very small and it's probably not going to blow up very big. But here we go. Oh, there's a gap in it, I can feel it. Well, anyway, this is why I'm not the expert craftsperson. But the interesting thing about glass, right, when I went to these glass blowers, and I had a little go and I made like something pretty simple, a little bit like this. And I couldn't take it away with me immediately because we had to do what's called annealing. So when you take glass out of a flame, if it isn't Pyrex like this, you have to do exactly like I did at the start by introducing it very slowly. You have to take it out of the flame very slowly as well. And that is because with all materials, actually, almost all materials, when you heat them up, they get a little bit bigger, thermal expansion, and when you cool them down, they get a little bit smaller. And this is because the atoms inside are getting all excited and they're vibrating around a little bit more, and they're taking up more space, and so the whole material takes up more space. It's kind of weird when you think about it. But one risk that you have, if you heat up this part of the glass really hot, as I've just done, and this part remains so cold that you can touch it, there's a big temperature differential across that material. And what can happen if this part has expanded loads and this part hasn't, is that loads of strain is set up inside the material, and eventually it could shatter. And we can actually see material strain in glass. I've got a different piece of glass to show you now. And we can see it because glass is a material that has lots of weird optical properties, right? We use glass for example, down cables to get the internet into our houses, and it's able to interact with light in lots of exciting ways. What I've got here to show you, if we can switch over to the projector. So, what's happening here? There's a light underneath, and the camera's up here. And I've got a cross-polarizing filter on here, which means that all the light coming up here, when it passes through that filter, it's a bit like, like slats on blinds in a house. It passes through those, and then it kind of goes into lots of little lines. I've got exactly the same thing here as a different sheet. And if I line this up one way, you can sort of see through it. But if I rotate it 90 degrees, no light goes through at all. Because we've gone through that way with this one, and that way with that one, and what happens is there's no light that gets through. What I've got here is a tempered glass screen for an iPad or something like that. It's made of glass that has had a lot of internal strain put in it. Because if you strain glass a lot, it becomes very, very hard, and it makes it less likely to break. Because if you've got if you've got the atoms kind of pushed together a lot, and you try to crack it, the force of those atoms being pushed together means that it's not likely to crack very easily. So that's what I've got here in a piece of glass. I'm going to put it in between the cross polarizers, and what you'll see is that it starts to let the light through. So that's very nice. But what it also does, glass is what we call a birefringent material, which means that it bends light. And so when it bends light, you'll be able to see, hopefully, as I move this material, as I strain it, you'll be able to see that it's bending light to such an extent that it's causing a lovely little rainbow through our cross-polarizers. And this is what would happen if I were to take my glass rod out of the flame too much. This sort of strain would go into it. And if you strain it too much, then it can cause a horrible shattering catastrophe, as I found, actually, with my test tube from the lab. And this is really important to the history of science, actually, which is why I wanted to start with this, talking about the Royal Institution, because science, or rather glass, is a material that it's always been a friend of science, right? From the lenses that we use in microscopes to see the very, very small things, to the lenses that we use in telescopes to see very, very big things. And chemistry labs, if you go into any lab, it's filled with glass. And the reason is that it's brilliant. Like, we can see through it, and we can see our experiments happening in it, and we can heat it up to very high temperatures. But that was really only the case for the last 150 or so years. Because before that, they didn't have a special type of glass that wouldn't do the expansion and contraction thing reliably. So before the 1880s, all chemistry experiments were like a little bit of a risk to your life, because you would be heating up your glass thing and maybe all of a sudden it would smash. And then in 1880, a guy called Otto Schott invented what's called borosilicate glass, which you might know as Pyrex. And Pyrex is designed to have absolutely no thermal expansion coefficient whatsoever. So that means that you can heat one side of your Pyrex dish as hot as you like at the back of the oven, and the other half can be like hanging out of the front of the oven, and nothing is going to go wrong. And scientists adopted this really, really quickly, because they realized that they could then have their experiments in stuff that wasn't then going to explode and like throw their dangerous equipment all the way around. So that's glass. Like I say, glass has had a very, very long and happy history with science. I don't know. Thank you. So when I first tried glass blowing, I was a little bit anxious because, this was a material that could blow up in my face. It was very, very hot, blah, blah, blah. And also there was this thing in the back of my mind of, this is going to involve some sort of creativity. There's a real crafts person next to me who's like a professional creative. And she was like, yeah, just make whatever you want. And I was like, I don't know what I want. I don't have any creativity. But what was good about glass was that because when you heat it up, it kind of flows and it sort of flops around on its own. You can actually make something that looks quite nice without knowing at all what you're doing. It will just kind of form something lovely. And because when you heat it up, it burns off all of the horrible finger marks and stuff. When you glass blow for the first time, what I found was that I was able to make something relatively nice relatively quickly. So that kind of bolstered my confidence as I went forth on my quest and had a go at other materials. So the next material I want to talk to you about is plastic. So the story of plastic is a story of my Polish granddad. You may have noticed on the way in that I've got a Polish surname. That's because of my Polish granddad. I grew up in Britain, in Bedford, and growing up in Britain with a Polish surname occasionally caused some embarrassment, like when I have to talk to people on the phone, spell it out, all those sorts of things. People pronouncing it, people having to spell it. It's been interesting, but it did have some advantages as well growing up. I can remember being the first in my class to disappoint everyone and tell them that Santa wasn't real when Santa Claus turned up in my house speaking with a really strong Polish accent. So that was my first instance of amateur sleuthing. And then Grandad George showed up 5 minutes later. But I always remember Grandad George as being a very kind of sort of very big figure in my childhood, but also quite a mysterious one as well. Obviously, he was an old man, as you can see. It's not Santa. By the time that I kind of was a child, and so I heard lots of sort of family whisperings of all of his life story, which had been kind of a lot of sort of family legends around Grandad George's life story. And when it came to think of a story to write for the book about plastic, I immediately thought of Grandad George, because Grandad George was born in 1910, which was just a few months after the first synthetic plastic called Bakelite that was invented in 1909 by a guy called Leo Baekeland in New York. And Grandad George lived to nearly 100, so he lived for basically the whole of the 20th century. And so from the birth of plastic and the birth of Grandad George, he sort of saw plastic take over our entire material world throughout the 20th century. And luckily for me, when I'm writing a book, Grandad George had written his memoirs, and we had a copy of them in the house. And so I sat down and I read through Grandad George's life story. And as I read through it, trying to find sort of material links, what I found was that his life story was constantly impacted by the material of plastic. And so the story of plastic for me is inextricably linked with the story of Grandad George. There are so many different stories that I could tell you of him. I could take a whole hour just on him. So I'll do the brief version for you. He was born in Moscow in 1910, as family legend has it, because his mother was there at the time. And he spent his early childhood in Moscow. When the Russian Revolution started to kick off, him and his family became refugees, and they had to flee to the east along the Trans-Siberian Railway. George was about 7 years old by this point. He had his younger sister and his mother and his father, and they were all on this refugee train. It was very, very slow. And around the halfway point through Russia, in a town called Novosibirsk, George became separated from his family. So in the middle of Siberia, in the middle of winter, 1918, in the middle of the Russian Revolution, George found himself completely on his own. And nearly a year later, he caught up with his family later down the line. That's another whole family story. But they eventually caught up with each other. They went through China and then to Japan, and he spent a few of his childhood years living in Japan before eventually returning to Warsaw, where he spent his teenage years. So teenage years, around the 1920s, there was lots of stuff starting to happen with plastic. The scene was being set, if you like, for plastic to suddenly become the massive material that it is today. 3 things happened. The first thing was the chemical recognition of plastics as a family of materials. So a guy called Hermann Staudinger, a German chemist, came up with the term, the idea, that you could have little molecules, which he called monomers, and you could then click these together like Lego in long chains, and those would be called polymers, and that process would be called polymerization. So in the early 1920s, him and others were working on the kind of chemistry of this stuff. And he worked out that you could have the same monomers all in a line, or you could have alternating monomers all in a line, or randomly distributed ones, or ones with branches coming off. There were all these this sort of big range of ways that materials could be, but all of them had in common that they were long chains. Added to that, you can have polymer chains that are in a wiggly, squiggly snake pattern, which makes a kind of crystal, which can melt, as we saw in the previous chapter, or an amorphous structure where they're all kind of like spaghetti, all mushed in together. There are so many different permutations for plastics, but what Hermann Staudinger did was recognize that all of them together behave similarly enough that you could call them a family of materials. So that was the first thing, the recognition of the chemistry of these materials. The second thing was the engineering of mass production. So the building of machines that could form and melt and extract the raw materials for this stuff, which set the scene for it to become a massive, massive industry. And the third thing that happened was brands got involved. So brands like Rolls-Royce and Harrods of London started making plastic stuff and marketing it to people as like the next new, amazing, futuristic type material. It was seen as a luxury at that point. So those three things were going on in plastics while Grandad George was living out his teenage years in Warsaw. He had always loved flying. He'd always been fascinated by aircraft. And he studied engineering, aeronautical engineering at Warsaw Technical University. After he graduated, he went on to go and work in what he wrote in his memoirs as an air screw factory, which is basically like a factory that makes aeroplane parts. And that takes us up in the story to 1939 in Warsaw, when, for the second time in George's life, he was in the wrong place at the wrong time and became a refugee for the second time in his life. And this time, he went south through sort of the Baltic states down to Greece. From there, he got on a boat to Marseille, from Marseille to Paris. And in Paris, he worked as an aeronautical designer, designing aircraft for the Allies. When Paris looked like it was going to fall, him and his mate Stan bought motorbikes and they were trying to get to British territory, but they couldn't go north. So they went south. They were trying to get to Gibraltar. At one point, I think they got arrested. Someone thought they were a spy or something. But anyway, they made it down to Gibraltar. But around Gibraltar was a military zone. No one could get into Gibraltar. But they only had Spanish transit visas that lasted 3 days. So with their visas running out, they had no other choice but to get on a boat over to the North African coast. From there, they took a taxi to Casablanca. And in Casablanca, George got on a boat that was sailing off into the Atlantic. Didn't know where it was going. And by this point, he only had a few possessions. They sold the motorbikes. And he had what he was wearing, right, the clothes that he'd been wearing for the last couple of weeks, some papers, a packet of cigarettes, and one luxury item, which was an inflatable mattress, like a kind of lilo, like you'd have at the beach. He had this inflatable rubber mattress. And this item, I think, tells us a lot about what was going on with plastics at the time. Because around that time, around the 1930s, still plastics were sort of on the rise, but we were still relying on the kind of the traditional ones that we'd been using for a long time, namely the ones that come from natural sources. So natural rubber that comes from the rubber tree, and silk that comes from silkworms. The principal two that were particularly useful for kind of the military as well at that time. But the Second World War presented a massive problem for countries that couldn't grow rubber trees, and for countries that didn't have a whole lot of silkworms knocking around. They didn't have these really important substances because all of the trade routes at that time were broken down. So chemists in Europe and places like North America were tasked with, can you create a synthetic version of natural rubber or of silk? And we see in the 1930s and 1940s a massive explosion in the invention of stuff like nylon and polyurethane, stuff that mimicked the natural stuff, but that you could make in a lab in Europe and didn't have to rely on trade routes for. So I always think of the Second World War as being a really pivotal moment for plastics because it's what really taught us how to mass produce stuff that didn't rely on natural materials. So Grandad George's rubber lilo mattress was his kind of prized possession on this boat. Like I say, he didn't know where it was going. It set off in the middle of the night. A few weeks later, he ended up in Nova Scotia in Canada. Some people got off the boat there. Grandad George didn't get off the boat. I don't know why. It came back over the other side of the Atlantic, and he landed in Cardiff docks in September 1945. From there, he came to London and worked for the rest of the war as an aircraft designer as well. After the war, it still wasn't really safe to return to Poland. He met his wife, he started a family in West London, and there weren't really that many jobs in designing aircraft anymore after the war. And so, resident in a relatively strange new country, he turned to a relatively strange new material in order to survive, and that material was plastic. Him and another Polish friend started a company making plastic goods, like everyday household goods. This is an advert for a coal bucket, which tells you a lot about the time, but made of plastic. And they called the company, by the way, Stewart Plastics Limited. Neither of them were called Stewart. Their surnames were very Polish. Harry Stewart was their foreman, their employee, but they called the company after him because even then they realized that the SEO of Ploszajski was not going to be good business sense for them. And I can attest to that to this day. So Grandad George started this plastics company. It went really well. They moved it to Croydon. They employed loads of people, and it allowed him to settle and thrive in this country that he eventually ended up staying in for the rest of his life. So during those latter decades then, the 50s, 60s, 70s, plastics everything turned to plastics, right? The textiles that people were wearing, the packaging that their food was being produced in. Even Grandad George's beloved aircraft eventually became plastic composites. And the reason was that in the post-war period, plastics were cheap, they were readily available, you could make them at home. Not home, but in the country. Don't try this at home. And so it kind of helped particularly countries like Britain get back on their feet after the war. And so Grandad George and people in his generation saw this transformation of the material world from textiles and metals and ceramics to ubiquitous plastic. And by the time that he died in his care home in 2007, everything around him had transformed into plastics, right? The carpets, the windows, all of his TV, the cups that he was drinking with, everything was plastic. And we know this now, of course, because we live in that modern world that is built of plastic. But it wasn't until I was born in the 1990s in that story that we started to actually realize that this may not be such a sustainable way of making stuff. Only in the 1990s did people start thinking, hang on a minute, we keep throwing this stuff away and it's just building up in landfill. And the plastics producers at that time were like, hang on a minute, we keep making this stuff and it keeps ending up in landfill and people are getting annoyed at us. So what we should do is tell them that they can recycle it and then we look good because it looks like a green material. But they knew even from the very earliest point that large-scale melting down of plastics to recycle them was never ever going to be economically viable. And I've got a little demo here to show you that demonstration. Yeah. Thank you very much. So what I've got here, I don't know if there's any Gen Zers in. This is a CD. We used to play music on these. And obviously made of plastic. This is the same thing, but that's had the aluminium shiny foil part scratched off. And what I'm going to do is I'm just going to heat it up and sort of show you. So when we talk about recycling plastics, we talk about heating them up, reforming them, and then making new fleeces out of bottles or whatever. That's not really what happens. So when you heat up plastic, you can try this at home if you're careful. When you heat up plastic, the intermolecular bonds break, those bonds between the molecules, and it starts to soften. The crystalline parts start to melt. And you can make like a beautiful jellyfish out of an old CD. This is not good for playing music with anymore, is it? And so when we talk about recycling plastics, and we talk about melting them down and making new stuff with them, what we can make with them is not that useful, really. The material's properties degrade, it becomes weaker and kind of pointless. I don't know why I did that. And so recycling has got a long way to go, basically. But the good news is that Well, the reason that recycling's got a long way to go, we saw earlier, right? Plastic isn't just one type of material. It's loads of different types of materials, and all of them have different molecular structures. All of the ways that the molecules are in there are different. All of the monomers can be different as well. You can also have additives in there like dyes. Once you do all of that, it's impossible, nearly impossible, to then kind of go back on that and get the raw materials out again. But technically, there's no reason why we can't do that. It's more, I think, a kind of societal problem of having to do all of the sorting out part first. There's no chemical reason why we can't really do recycling. And I'm actually quite optimistic that, although this looks quite bad, the problems that I've described to you are not problems that material scientists aren't used to solving already. So I'm pretty confident that we will kind of sort out this waste problem, but it is going to be a massive problem for our generation. And it's one that I hope with sort of engineering geniuses like Grandad George, we will solve that problem together. But it also kind of shows us that science isn't just a kind of scientific problem, it also interfaces with societal problems as well. And that's what I learned from plastic. Okay, let's talk about steel. Steel is kind of a titan of the material world, at least in material science undergraduate courses. We spend so much time talking about steel. There are still people researching new things to know about steel, even though we invented it over 100 years ago. It's because it's so industrially important. It's also very materially interesting. But my first exposure to steel, other than learning about it in my undergrad labs, was my impression of it was that it was a very kind of macho material. It was a very kind of, because it's tough, it's strong, it's engineering, blah. That's what men sound like. That was my first impression of it. The reason that was my first impression was that my first sort of real life exposure to steel was here. These are the Bonneville Salt Flats, which are on the border of Utah and Nevada. And in the summer of 2011, while I was in my second year of university, I got the chance to be part of a landspeed racing team who were attempting to break landspeed records on the Bonneville Salt Flats. And the team that I was with, we were trying to break the record in this car. This is a 1-litre Streamliner engine car. Streamliner means that the driver is like this in the front. 1 litre is very small. It's actually a motorbike engine that was taken out and put in this car. My first car was a 1.2 litre Fiat Punto that would scream at me if I went above 65 on the motorway. This car, smaller engine, we were trying to get it above 313 miles an hour. So, massive engineering challenge. The other challenge was that on this team was me, age 20, long blonde hair, vegetarian, studying for material science at university, and then 5 Glaswegian car mechanics. So the team dynamic was a little bit strange, but we were all united in this task of trying to break this land speed record, and we had only 7 days to do it in. So we camped out on these salt flats for a week, and every day we'd be working on this car, trying to push the engineering components beyond their limits, really, to try and get it to go really, really fast. We had various, I would say, teething problems to start with. Wrong fuel in the tank. We've all been there. What else? Oh, wrong plug in the wrong socket. At one point there was an electrical failure, which meant that there wasn't any brakes, because the brakes are just parachutes that fly out the back, and that's triggered by a little button that apparently wasn't working. So those sorts of things. But by day 4 of 7, we were starting to kind of get into the groove of it and starting to get fast. And so on one particular occasion, an attempt at the record on day 4, the driver took the car from first gear to second gear, going fast, second gear to third gear to fourth gear, and then something in the engine went bang. Can I get a rim shot, Joe? Yeah. Atmosphere. Something in the engine went bang. So the driver came to the side of the Salt Lake, and we got the car back to the pit stops and opened out the engine. And out of the engine fell a kind of waterfall of glittery black engine oil. And I was informed by the real engineers that engine oil shouldn't be glittery. The glitter in that engine oil was what had previously been the components of the gearbox, now shredded on the beautiful white crystalline ground. Which constituted a problem. So I wandered over and I picked out two tiny little pieces of metal. I've taken a photo of them here for you. And I sort of wiped the engine oil off and I noticed something very interesting. These are like probably about a centimetre long. And what they are is, like, if you imagine a gear cog, like a circular gear cog, and there's lots of little like ridges on it, these are those little teeth. Each one of those is a ridge that had been kind of stripped off of fourth gear. And I noticed something very interesting about these. The first thing, if you look at the fracture surface on the right-hand side there, that's what I would expect steel to break like. This very much looks like what is called ductile fracture. In ductile fracture, when materials like steel break, they kind of, if you see it in slow motion, they kind of pull apart and they sort of bend and flow a little bit before they tear, and you end up with a very sort of rough fracture surface. Now, you will have experienced this sort of fracture if you've ever tried to share a Snickers bar with a friend. Why would you share? No. If you have ever attempted this, right, if you try and break a Snickers bar, it doesn't snap, right? It kind of pulls apart very slowly, and you end up with like a very kind of rough fracture surface. You can picture the scene, I'm sure. So this is how I would expect steel to break as well, a very sort of rough fracture surface. Fine, that's what I would expect. But the mystery came with the other little gear cog tooth thingy. On the other one, you can see that the fracture surface is flat and shiny like a mirror. This should not have happened, right? Because this very flat and shiny fracture surface is like what you would expect if you broke a piece of dark chocolate. I should have unwrapped these before. If you break a piece of dark chocolate, as you know, it just snaps, right? And you end up with a very flat fracture surface. That's brittle fracture. So that's a mystery. That was really weird. Why did one of these pieces of steel, identical materials, one break like ductile fracture and the other like brittle fracture? Well, there's two possible explanations. The first is temperature. Because if you break what are normally ductile materials, when they're extremely cold, they go through what is called a brittle to ductile transition. So at room temperature, they can be ductile, and if we could have the dewar, invented by James Dewar, of liquid nitrogen. Thank you very much. Thank you. Thank you. We're going to take a little Snickers, and we're going to stick it in the dewar invented by James Dewar in this very building of liquid nitrogen in here. And it's just going to cool down for a couple of seconds. And we're going to see what happens when it breaks. Oh, that's a big hammer. It's bigger than the one we practiced with, that's fine. So it takes a little bit of time to cool down. I can see the liquid nitrogen is bubbling away in there. I actually don't know where it's gone. This is a really fun game. Should probably use this other glove. Should we have some more music to accompany this really quite boring...
1, 2, 3, 4.
I found it. Okay, so what we're going to do is we're going to see what happens when a ductile material gets very cold. Oops. It's like that game. You've ever done that? Anyway, doesn't matter. Ready? Should we have a countdown? 3,
2, 1.
Yeah, turns very brittle. Turns very brittle indeed. Steel does the same thing, by the way. When you cool steel down to very, very cold temperatures, it turns brittle in the same way that a Snickers does as well. We tried this earlier with a steel bar. I wasn't strong enough to break it, but on the Titanic, the reason that the Titanic impact with the iceberg was so catastrophic was that the steel that the ship was made out of had gone through its brittle to ductile transition. So when it hit the iceberg, it didn't just dent like it would have if it was a bit warmer. It would have shattered like our poor Snickers bar here. So that is the story of Jack and Rose, unfortunately. It's all to do with the brittle to ductile transition temperature, if someone could call them. I solved it. So yes, so that's one option, right, is temperature. But of course, our gearbox components would not have been wildly cold like this. So the only other option, the only other solution to this mystery was the speed at which, I've got loads of Snickers under here if anyone wants to, was the speed at which the gear cog came off. Because if you break a Snickers bar very, very, very quickly, it does the brittle thing and not the ductile thing. Temperature is also slightly a factor, and I'm thinking now that maybe this is going to be too warm. So I'd say this has got a 50-50 success likelihood, but we'll find out if it works. So what I'm going to do is I'm going to try and break the Snickers bar very, very quickly off the side of this. And hopefully what we'll see is that it will turn from a ductile material into a brittle material. I'm going to need a countdown and a very steady hand. Ready? 3, 2, 1. Yes! I don't know where the other one, but it's here. I'm not going to pass this around in case anyone's got a nut allergy, but you heard it snap, right? It didn't do the ductile thing, it did the brittle thing. And these fracture surfaces are like flat and shiny like a mirror. So this is what I think happened inside the fourth gear, is that one of these components came off, probably the ductile one, came off slowly like normal, bounced around inside the gearbox, smashed into number 2. It didn't have time to do the ductile bending, flowing thing, snapped off like a piece of dark chocolate, or like a Snickers bar karate chopped off the side of a thing. Now, that was my first exposure to steel out in the real world. A relatively macho environment. We obviously didn't fix the gearbox because it was very much like the Snickers bar, actually. So we had to borrow another gearbox from one of the other teams. After the 7 days were over, I think we eventually got up to about 278 miles an hour. But I believe that the record of 313 still stands. So if anyone's interested, that record is there to be got. But that was my first exposure to steel, was this kind of macho environment. And when it came to thinking about trying blacksmithing, the craft of steel myself, I got very lucky. I was listening to Women's Hour in the lab one day, and I heard they were talking about steel, and I was like, turn that up. And I heard a woman called Agnes Jones who was talking about being a blacksmith, and you would have met Agnes earlier. I very embarrassingly fangirled her online, and she very generously came down to London. We chatted on my podcast, and then when it came to the book, I went up to visit her in Glasgow, and we had an amazing day blacksmithing together. It was so much fun. I made a very wonky poker and a little hook to put in my camper van. What I'm going to do is I'm going to show you a little bit of blacksmithing. You've seen things snap. You've seen things get brittle and be ductile. And obviously when we're doing blacksmithing, what we're doing is we're really trying to get into that ductile area, right? We really want to get it as soft as we possibly can, because steel in itself is a very, very hard and strong material. So, right. So, heat a bit of steel. Should we have some music for this? It's going to take a couple of minutes. It's quite a short one, that one. Amazing. That's actually perfect timing. So what I'm looking for here is the metal to get hot, obviously. And blacksmiths, Agnes told me, know the temperature of their steel by the colour that it glows. Because at around 500 degrees, materials like steel will start to glow red. And then at around 1,000 degrees or so, they'll start to glow orange. And the hotter you make them, the kind of further down the rainbow they go. So they start at red and then orange. And if you've ever been to primary school, you'll know that they then turn yellow. And eventually, the hottest materials will turn blue. And the hottest materials will like overshoot the visible spectrum and go into the infrared spectrum. And that's why we get sunburned, is because the sun is so hot that it exudes ultraviolet radiation as well. But this isn't as hot as the sun. This is probably around 1,000 degrees now. And around that 1,000 degrees, steel will be easily soft enough for even a terrible amateur blacksmith like me to make a small and tiny dent in it. So where's my hammer? There it is. Ah, it's still Snickers. It's going to be smelly. It's gone very slightly flatter, everyone. Yeah, look, the day that I spent with Agnes was obviously a lot more impressive than this. Under her guidance, even my amateur hand made those beautiful objects. But the point really is that, I don't know where to put this. Don't touch that, everyone. My first impression of steel as this kind of macho engineering material, doesn't have to be the case, obviously. You've seen Agnes's artwork out there, right? It's beautiful, it's aesthetic, it's curved, it's not the kind of macho stuff that I had initially met. And when I wrote the story of steel for my book, I sort of wrote the story of the women behind the steel industry. I was researching for it and I went up to Sheffield, which is a massive steelmaking town in England, and there's a ironically bronze statue in in Sheffield town centre called Women of Steel. During the Second World War, the women of Sheffield went into the steel factories to continue the work that men couldn't do because they were on the front line. And after the war, they basically just kind of got displaced by the men who came back, and then they had to all of those skills were lost. And so this statue in Sheffield Town Centre kind of shows you, commemorates their knowledge, their expertise, and their time working in the steel factories as well. So I think this kind of shows us, well, what I learned from steel certainly was it's not just the materials that are around us, it's the kind of stories of the people that make it and that manufacture it and that have kind of come before us as well. Let's talk about brass. I first met brass when I was in year 6, and in our music lesson at school, my music teacher said, we're going to have a demonstration from the school's new brass teacher. And I thought, here we go. Some loud old bloke blasting our ears out with a trumpet. And no sooner had I had that thought, but the most glamorous person I've ever seen in my entire life walked through the door holding a trumpet. She gave us a 15, 20-minute demonstration of everything that a trumpet can do. And by the end of that 20 minutes, I was like, I want to be exactly like you, and I need you to teach me how, please. So from that day forth, I picked up the trumpet. And it was a material that I couldn't not write about in the book, because music has been a huge part of my life, as you can see, for a very, very long time. And one of the demonstration that Sarah Wilson, that was her name, that this trumpet player did. Sorry, I'm just trying to find my demo. Here it is. It's absolutely fine, don't worry. No, that's fine, thank you. So the demonstration that Sarah did was, well, funnily enough, it demonstrates that materials are not actually that important at all, because you can make a pretty convincing trumpet out of a hose pipe. So you can make a pretty convincing trumpet out of a hose pipe. It's not that in tune, but it gets a little bit better if you put the plastic funnel on the end. Sounds a bit more trumpety then. Yeah, so materials are not that important. You can make a pretty convincing trumpet out of a hose pipe. But this hasn't got any buttons to press. But even with a hose pipe, you can make like quite a few different like pitches of note. That lower harmonic is really horrible. And the way that this works, right, I think is it's really, really interesting, and I'm going to show you how. And then I'm going to demonstrate it for you in a little bit more of a dangerous way. But first, let's talk about harmonics, right? Because that's what you're hearing. You're hearing what are called harmonics. It's different ways for the air to vibrate inside this tube. An easier way to understand this is actually not with tubes, is with strings, because you can kind of see them. So Raj, if I can invite you, please, to come up. Thank you very much. Welcome, Raj. Raj, what I'd like you to do is just to play an open string. Okay, this is what we're seeing up here, right? This open string is vibrating as Raj plucks it. It's vibrating up and down, and then that's transferring into sound waves, which is what we are hearing. But on a string, you can make that string vibrate in different ways, which are called harmonics. And Raj can do this by doubling the frequency of the string, by encouraging the middle part of it to not move, to kind of form what we call a node, if you like. So Raj, if you can play us the first harmonic, and then the open string. Right, so that's like an octave between, right? So you're doubling the frequency by halving the length of string that is vibrating. And there are loads of harmonics that exist. You can do this with thirds and quarters and fifths in lots of different ways. Very nice, thank you. So these different ways of vibrating create different notes, and it's these that the hosepipe trumpet is tapping into. Now, the difference with a pipe is that with a string, you've got the two ends of the string that are in a fixed position. With a pipe, the end that your mouth is at is closed, because your face is on it, but the end with the funnel is open, because there's a funnel. So with a pipe, it's different. With a pipe, you have a closed bit at one end and an open bit at the other. But the same thing applies. We can make, in the same way that Raj made his string vibrate in different ways in different harmonics, we can do the same thing with the air inside the tube. The difference, though, is that because we're open at one end, some of those harmonics are not available to instruments like the trumpet. So we have only every other harmonic available to us. And that's why there's some like quite big tonal gaps in the trumpet's repertoire. Now, that's the kind of information part of this. I'd now like to demonstrate this in a little bit more of a dangerous way using fire. Yay! I promised you propane. Right, I'd like to introduce you to my hand-built Rubens tube, which... Oh, yeah, carrying the propane as well. Not anymore. Propane's gone. Right, ready? Yeah. Right, this is my hand-built Rubens tube. I built this a few years ago by going to a plumber's on Tottenham Court Road, asking them for a big, long pipe, drilling loads of holes along the top, fitting a gas fitting to one end and a little rubber membrane at the other. What we're going to do is we're going to fill this with propane. It's basically like a big long gas hob. Ooh, that was quick. Is it anyone's birthday? Gosh, that's very warm. Okay, lovely. Okay, so this is called a Rubens tube. Invented by Rubens, but not that one. And what this is a pipe that is the same length, well, 1.5 times the length of a trumpet, actually, and a series of holes along the top, and through those holes are little flames of propane. Now, what happens when I play sound down here is that the rubber membrane will transfer the sound from my trumpet into the propane, and the propane will form those sorts of standing waves that we saw in the instruments. And standing waves, sound waves of all kinds, are fluctuating areas of high and low air pressure. But in the case in here, it's fluctuating areas of high and low propane pressure. And so when you have that, you have some flames that have got a lot of propane pressure and some that have a small amount of propane pressure. And what you see is sound waves in fire. So I'll give you a little demo. Let's just play some open harmonics first. So, it was no one's birthday. Okay. So you can see, so the same thing is happening that was happening in Raj's string, but is happening in the propane in here. Should we play a tune?
Yeah. 1, 2, 3.
No. So, what's all this got to do with material science? Well, we can, let's keep this lit for a minute. We can understand sort of how material science interfaces with society, with culture, through kind of the history of the trumpet, because the trumpet has evolved as metallurgy has evolved throughout history as well. So trumpets have been around, like they were one of the first instruments, right? Conch shells and didgeridoos, like anything that you could find in the natural world that you could blow down and make a sound constitutes an early trumpet. And by the sort of ancient Egyptian kind of era, trumpets as instruments, mostly instruments of war, like military instruments, were used. That's because they were loud. They had these distinct harmonics that you could play, which you could convey signals with. And they're also like loads of cursed trumpets throughout history. This is the silver and gold trumpet out of Tutankhamun's tomb. What you can see, the top one there is the silver and gold trumpet. The bottom one is the kind of thing that they put inside it so that if you dropped it, then it didn't dent. Because silver and gold, although they were very, very valuable materials, befitting of a king, are not good materials for trumpets because they're very, very soft. So you needed to have your little trumpet inner in there every time that you weren't playing it. So silver and gold, then, we can see, are metals that we were able to dig out of the ground. They exist as themselves in nature, and silver and gold were some of our first metals that humans kind of ever really started to use. Then the Bronze Age came along. Around 5,000 years ago, we started to invent new materials that hadn't existed in nature before. And we started making trumpets out of them very, very quickly. And so bronze was a material that was an alloy. So we started mixing different types of metals together to make them stronger and sharper and tougher. And we made all sorts of kind of, I guess, weapons out of those, but also trumpets. And by this point, the shape of it is the same. It's basically just a great big long tube. And so the only notes that you could play on a trumpet like this would be like the same harmonics that you've heard before. So that's all you could do. And so really it was just kind of military stuff that people did. That kind of stuff. For a very, very long time. By the Roman period, we had brass. And brass is what's called a sonorous material. It kind of is very good at supporting the vibrations and sound. And we started to make trumpets out of brass. Now, by this point, music was moving on a little bit. And like sort of organized music, the kind of classical period was coming about. And so melodies were starting to become important. And the problem for trumpets, though, sitting at the back of the orchestra, was that they still only had those same few notes. And so you never got the tune, which was really annoying, I imagine. I don't know, I wasn't there. But you never get the tune as a trumpet back in those days. And so what they did was they started to put little holes along the length of the trumpet, a bit like how kind of wooden instruments have, in order to change the length of it. And then you could start having, a bit more music that was actually musical. Etc. Right? Melody, tunes, woohoo! When you started having holes in trumpets. Everything changed with the development of, well, firstly being able to bend pipes. That was quite an instrumental, development in metallurgy, but also being able to do kind of finer details. So we're not just talking tubes now, we're actually talking sort of mechanisms. And this is a trumpet from the sort of late 1700s, and it was what was called the keyed trumpet. And the keyed trumpet had enough intricate mechanisms, we were able to master metallurgy enough to be able to basically add all of the different notes from that the keyboard has access to, but now into a trumpet. And composers like Haydn and Hummel, they started writing trumpet concertos to celebrate this new technological feat. And I'll see if I can remember how this one goes. Which way am I going? Etc. So the trumpet had gone, thank you. The trumpet could be lyrical, the trumpet could have colour, the trumpet could have the tune finally, and be just as kind of expressive as all of the other violin-y people at that point. So trumpets and metallurgy and engineering was all keeping pace with how music was changing as well. And we get to the trumpet that we have today as a result of the Industrial Revolution. Because with the Industrial Revolution and with the invention of the steam engine is just a load of valves. Steam engine had them first, and someone had the bright idea of sticking valves onto a trumpet. That made the switching of the notes really easy, and it made the modern era of music accessible to trumpet players, from the kind of romantic period to the jazz period, and then to the funk and soul period. Now, I need to move on. Well, the final point that I will say, basically, is that materials engineering, they were inextricably linked with kind of culture and how culture was changing and society. And we can see that all in kind of the engineering of trumpets. But the final thing that I want to say about trumpets, as we saw with our tube, the material of the trumpet isn't actually that necessary, isn't that important. And thanks Dan, one of the silly ideas that I had for the wonderful demo team at the Royal Institution was to say, how important are materials to trumpets? And shall we see what we could make a trumpet out of? So I can't take any credit for this at all. This is all the wonderful demo team. There's a few world firsts about to happen, guys. This is actually just a plastic trumpet. This isn't anything particularly special, but this was our starting point. So have a listen to this. A very basic sort of trumpet. Okay. Like I say, I tasked the wonderful Royal Institution team with how much we could push this idea that you can make a trumpet out of anything. So, allow me to introduce you to the world's first chocolate trumpet. Now, the experiment is, does it sound exactly like that one? So have a listen. Sounds the same? Sounds exactly the same? Oh, it's so silly. Concrete trumpet. Does it sound the same? Concrete sounds the same. Oh no. Jelly trumpet. Does it sound the same? It really smells delicious when you play it as well. And finally, I actually haven't seen this one before because it's been in the freezer. Ice trumpet. Mm-hmm. Oh, it's quite slippery. Does it sound the same? That's actually very beautiful. Does it sound the same? Dan, come and take a bow. Come and take a bow. My goodness. Who'd have thought it? Right. Going to skip that material. Final one. Material of sugar. In the summer of 2018, I found myself standing on a beach called Shakespeare Beach near Dover with my arm up like this, ready, just waiting. Slightly off the shore, about as far away as the back row are there, was bobbing a little boat. And on that boat were my crew members that would be assisting me as I attempted to swim the 21-mile span of water from England to France. While I was standing there, looking at this enormous ocean in front of me, I was hoping that I'd done enough training. I'd spent every weekend that summer down in Dover practicing swimming for hours and hours and hours on end. But I had one material on my side in this endeavor. And that material was encased in chocolate mini rolls. It was sloshing around in energy drinks. It was dissolved inside a little gummy bear's tummy. Because these sorts of ridiculous endeavors require a lot of energy, a lot of refueling. And so the material that I had on my side was the material of sugar. So as I was standing there on Shakespeare Beach, waiting, I was thinking about all the sugar that was on board and thinking, I hope I've brought enough, and also my passport. And as I was thinking these thoughts, a siren went off on the boat, and I knew that that was my cue to wade into the water and to start putting one arm in front of the other and attempt to swim to France. Now, let's have a little look at sugar. Sugar structured the swim from start to end. One of the classic questions that people often ask is, do you have to stop to rest? or to eat something. Rest? No. Eat something? 100% definitely all the time. So we stop about once every hour in a channel swim to consume, hopefully, enough energy to get us across. Now, sugar comes from plants, from the process of photosynthesis. You may have learnt this at school. But not all sugars are equal. As I learned in my extensive research while I was training. Now, let's be material scientists about this. Let's zoom in and have a look at what the atoms are up to inside sugar. This is a molecule of sucrose. Sucrose is the sort of sugar that you would have in your kitchen cupboards at home. Pretty standard sugar. And what I want you to notice is the shape of the molecule. Right? There are two kind of rings of atoms that are joined with an oxygen in the middle. This is a relatively small molecule. And we know this because when we eat sugar, we get the energy out of sugar really, really quickly. Our body is able to break down that small molecule, like, bam, done it, here's the energy, which is wonderful. It's really, really useful. I'm going to reuse the trumpet demo to show you exactly how accessible this energy is for us. So, more fire. Protect the floor this time. What I'm going to show you is exactly how accessible the energy of sugar is. So what I've got is just like a very standard icing sugar that you can buy, that you'll probably have in your kitchen cupboards at home. And I'm going to put it into the funnel trumpet. And I want you to watch what happens when it burns. Oops. There's probably a better way of doing this. Ooh. Don't talk while you do that. Okay. You have to do the countdown. Okay, ready? Hang on, not ready. Okay.
3, 2, 1.
Yes, thank you. Right. Sugar, like sucrose, lots and lots of available energy, right? It's really easy to burn, and that kind of is what happens in our bodies as well. We can break it down really quickly and access that energy. But you don't want to be doing this in a channel swim, because in a channel swim, you might be swimming for 14, 16, 20, 26 hours at a time. You don't know how long you're going to go on for. And so you don't want to have a really sharp, sugary energy spike and be like, woohoo, I can swim for days. And then like 10 minutes later, be like, ugh. And so what we want to do is to eat different types of sugars that will release their energy over a bit of a longer time. The sugar of choice for channel swimmers is called maltodextrin. The molecule of it looks like this. And it's a much, much bigger molecule. And you can tell that because there's little brackets around the sugary ring. There's an N there, and it says that N is greater than 2 but less than 20. So maltodextrin molecules have up to 20 of those sugary rings in a great big long molecule. And that means that it takes a lot more time for our bodies to break down those molecules and access that energy, which I will now show you again with the same experiment, but with a little pot of maltodextrin. So, same thing, stick the glove on, empty out the rest of the sugar. Okay. I want you to watch how differently this burns. Okay, ready with the countdown?
3,
Thank you.
2, 1.
Huh. An interesting scientific result. That's what I was expecting to happen. And I was expecting it to happen because this is a much, much bigger molecule, right? So it takes a lot more for this molecule to burn, right? Even a blowtorch can't burn it in this very scientific experiment. And that's kind of not exactly what's happening in our bodies, but it's sort of similar. Our bodies take a lot more time and energy to break down these molecules. And so the energy release that they give us happens over a much longer time period, which is great when you are attempting to swim for hours and hours and hours on end. In my channel swim, I had maltodextrin as sort of dissolved in liquid, and my crew would throw it down to me every hour, and I would drink it down and then swim on every hour, after every hour, after every hour, after every hour. There's one more really cool thing that I want to show you about sugar before I talk to you a little bit more about the swim itself, and that is to sort of take us back to what I said at the start about what material science is and how it can show us how the material world around us is made. This is literally, I just got a microscope, got the sugar out of my kitchen cupboard and had a look at what it looked like. And so this is just like loads of little grains of sugar. But if I zoom in on one of them, you can see something that I think is unbelievably amazing. Right? This little sugar crystal looks like a gemstone. Right? If I emphasize the corners of it for you, you can maybe see it a little bit better. This is a single crystal of sugar. And it's in this shape because of the way that the atoms and the molecules are arranged inside that material. So every single molecule in there has lined up exactly in the right place next to its neighbor. And millions of them have coordinated themselves and done that. And they've grown in a way that makes the shape of this crystal. So we can see from the shape of this crystal what's going on inside the atoms and the molecules that make it up. And so when I see things like this, I see that we can peek past the curtain of how the material world is made. This kind of demonstrates to us, to me anyway, the fascinating link between what we can't see and what we can see. And material science has really opened my eyes to exactly that, to how these tiny, tiny building blocks of matter result in the incredible material world that we've built ourselves. So I ate sugar every hour, on the hour, and I was counting down in my head until after about 9.5 hours, when I would say that I ran out of sugar, at least mentally, and had what is known in the industry as a sense of humour failure. Luckily, though, at that point, or shortly after that point, the sun came up. And I found myself swimming into the dawn in the middle of the English Channel. And that sense of humour, fortunately, was very short-lived. A few hours later, I got the money shot. If you ever do swim the channel and you don't get this picture, you have to go and do it again. I will let you read the book to find out exactly what happened at the end of that story. There are some for sale in the foyer. All right, let's play our last thing. Where can we end this? Well, I set out at the start of this story to become an expert in materials by chatting to craftspeople, by trying to learn from them, learn their hand skills that have been passed down over the generations. What I found was that the more I learned from them, the less expert I became in a way, because I realized that the more the more knowledge base that there was that I didn't have. But that for me is kind of the joy of it. And that is sort of what it feels like to be a scientist, actually. The more you learn, the more you realize quite how much there is out there to master. But what I hope that you've got out of this evening is by me showing you the stories of the ways that materials have intersected with my life, you'll start to notice the way that materials have intersected with yours as well. Might not be trumpets, might not be sugar, but open your eyes to this, because this is the stuff around us, and this stuff really matters. Like, it really does. We saw in our chapter about plastics how there are really huge problems that we have as a society that involve materials and involve working together and solving these problems together and changing how we behave. So all of this stuff is inextricably linked, and I hope that tonight has given you a little bit of a glimpse into that. So I will end there. Thank you so much. I've been Anna Ploszajski.